So the parts that are within the grip could be 1 or 2 or 3 or more members. As we tighten the nut, we're going to put these members in compression. And the compression goes in a member at an angle, so portions away from the head are still going to see some compression. And we said we can model this using a frusta, which is like a part, a top cut off as they get compressed. You're as if looking at a cone with the top cut off. So what you're seeing here that looks like a trapezoid, if you are looking in 3D, you are looking at something like this. Where I have this uppercase D, this is equal to the diameter of the washer or the head of the bolt. And typically this uppercase D, the head of the bolt, is equal to 1.5 times the diameter. Typically, uppercase D is 1.5 times the diameter. And when I look at this cone, we are looking at an angle, the apex angle. The apex angle ranges about 60 degrees. So half the apex angle alpha is about 30 degrees. So each frusta has a half apex angle alpha, as shown here. The frusta spreads from the bolt head and nut to the midpoint of the grip. So this is the midpoint of the grip. That's why this distance is L/2. So in order to find the member stiffness, we need to find the stiffness for the frustum in compression. And I'm going to have more than one frustum. And if I calculate the stiffness for each of them, then they all behave like, again, springs in series. Okay. So in order to find the stiffness of a frustum, we are going to look at a tiny piece that has a thickness dx. And the reason we're going to take a differential segment of it is because the area is varying. I don't have the same area throughout, so I cannot use the stiffness formula right away. But if I look at this differential portion of it, I can calculate the change in length of that portion, the dx, by saying that this is equal to P, and the length of it is dx divided by EA. The area of this part A is given by pi times r naught squared, the outer radius squared, minus the inner radius squared, which may be given as pi multiplied by, depending on this x depth, I'm going to multiply that by 10 alpha and add to that for the outer diameter. I'm going to use uppercase D plus lowercase d divided by 2. Actually, if I don't skip a step, I will go here pi and then use the outer radius as x tan alpha plus d over 2, that's squared, minus the inner, which is d over 2 squared. Okay, when I expand that, I get pi multiplied by x tan alpha plus d over 2 multiplied by x tan alpha plus d minus d over 2. When we want to find the total delta, P is a constant, E is a constant, pi here from the area is a constant. And I'm going to get an integral from 0 to L of dx divided by this term here, which we are going to have it as x tan alpha plus d plus d over 2 multiplied by x tan alpha plus d minus d lowercase d over 2. When we complete the integration, I'll find that delta is equal to P divided by PE times D tan alpha multiplied by ln 2T tan alpha. This is the integration from 0 to t. This is where the t is coming. Plus d minus d times d plus d divided by 2t tan alpha plus d plus lowercase d multiplied by uppercase d minus lowercase d. If I know delta for the frustum, I can find the stiffness K as P over delta, which end up being pi E D tan alpha divided by ln 2T tan alpha plus D minus D times D plus D, which is the numerator here, divided by 2T tan alpha plus uppercase D plus lowercase d multiplied by D minus D. And this is equation 819 in your textbook. Now, for a typical alpha, equal 30 degree, we can find K as equal to 0.5. So I simply substitute for alpha in equal 30 degree. 0.5774 multiplied by pi E times D. Of course, where E is the modulus of elasticity of the material within the frust, divided by ln 1.155 T plus uppercase D minus lowercase d multiplied by uppercase D plus lowercase d. This divided by 1.155 T plus uppercase d plus lowercase d multiplied by uppercase d minus lowercase d. So this is for alpha equal 30 degree. And this is equation 820 in your textbook. Now, please keep in mind that I have here my first frustum within one member. Then I can have another portion within a second member and a third portion within a third member and so on. So in order to find the total stiffness on the member, we combine all frusta as springs in series. So we are gonna get 1 over Km is equal to 1 over K1 plus 1 over K2 plus 1 over K3 and so on up to the last frustum, Ki. If all the members within the grip are made of the same material, all are made of the same material within the grip, then when I look at this combination, so if the grip consists of any number of members, but all are of the same material, if that's the case, I would just add 2 frustum. So basically using L over 2 and L over 2 because it's all the same material. So here I'm going to have 1 over Km is equal to 1 over K1 plus 1 over K2. And this is going to give me, and of course, K1 and K2 are going to be the same. So if I do that, I can come up with the entire joint can be handled with one equation. Km is going to be equal to pi E D times tan alpha divided by 2 ln L, which is now the grip length, tan alpha plus dW minus D, where here I'm using dW for the uppercase D, multiplied by dW plus D, divided by L, thank you, L tan alpha plus dW minus, sorry, this is a plus, lowercase d, multiplied by dW minus D, where dW is the washer face diameter. Please note that when I was looking at equation 820 and 819, I left D because there are going to be instances when some of the frusta are not going to have an outer diameter that is equal to dW, right? Like for example here, if I go to the second frusta, my uppercase D goes from this point to that point. So we're going to have to calculate that using the geometry, as we're going to do in one of the examples today. If we use a standard washer face diameter, dW is equal to 1.5 D. And I continue to use alpha equal to 30 degrees. If I substitute in this equation, by the way, this is in your book, is equation 821. If I substitute in 821, I get that Km is equal to 0.5774 times pi times E times D divided by 2 ln multiplied by 5 multiplied by 0.5774 L, the grip length, plus 0.5 D divided by 0.5774 L plus 2.5 D. And this is equation 822 in your textbook. So again, in this equation, we are looking at compressed members, all made of the same material. We're using an apex angle alpha of 30 degrees, and we are using a washer face diameter of 1.5 D. So all what is going to be required here is to find the diameter of the bolt, the grip length, and the modulus of elasticity. And I can use equation 822 to find the stiffness of the members. So should all the members be of the same material? And the apex angle alpha is 30. Equation 822 is one equation that gives us the stiffness of the member. So now we have an equation for Km and equation for Kb, and we should be able to calculate the stiffness of the bolt and the stiffness of the member. Again, these stiffnesses are needed in order to understand when I have a connection that is subject to an external load, what's the portion of the load that is going into the bolt, and how much of the load is going into this compressed member. This external load is going to try to further stretch my bolt and try to uncompress the members within the grip. Now, how good are these stiffnesses as compared to the ones calculated from a finite element model? A study has been done, and for a common material within a grip, finite element model agrees with the Frustum model with a 30-degree angle. So if you look at this triangular here, compared to the graph with the square for the finite element analysis, you see here there's the one with the square, and here is the one with the triangle. So they very much agree with a finite element model. When we did some curve fitting to the results from the finite element model, exponential curve fit, gave us equation 823, where the stiffness of the members divided by the modulus of elasticity divided by the diameter may be expressed by the coefficient A times the exponent of BD over L, where B is another parameter here, and L is the grip length, and D is the diameter of the bolt. Now, A and B depends on the material used. And in this table 8.8, we are given the values for A and B for steel, for aluminum, for copper, for gray cast iron, and for general expression. So I can use equation 823 to find the stiffness using the finite element model approach. Please remember, this is good if, or for the case of common material within the grip. So that's why this would be comparable to equation 822 that we were just looking at.